pausing here. There we go. So we're, kind of where we finished last time was saying that, if we decided, let's say we had an alternating series that definitely converges. It would converge to some number, right? A sum. But we certainly could approximate that sum by, cutting off the series at some point and doing a partial sum. But then the question would be, how bad is that, or how good is that? How far off would we be? And so what we decided last time was that maximum error was going to be less than or equal to the first neglected term. The reasoning for that was that with each successive plus minus term, that error would get chopped off just a little bit, canceled out by the opposite sign. And so the most you could be off would be that next term, the first neglected one. So that's what this is basically talking about here. Let's just kind of highlight and look at a couple of the terminology and the symbols of this thought. So the partial sum, if it's being used to approximate the actual sum, then you'd get a remainder or an error of the actual sum minus your approximation, right? Like if you knew the exact sum and then you knew your approximation, the amount that you're off would just be the difference between the two, right?
Yeah.
Okay. And so then that then is less than or equal to the a sub n plus 1 term. And so a sub n plus 1 just means the next one.
Yeah.
The first one that you chopped off, the first neglected term. Another way to think about it, I wrote up there, if you use n terms to find a partial sum, the remainder or error will be less than or equal to the n plus 1 term. And then we notice all the absolute values and the symbols there. We disregard the positivity or negativity of that n plus 1th term. So got a little example here that'll take us through kind of everything about alternating series, this number 1 here. So it says, for this series right here, does the series converge or diverge? Converges. Okay, so if we had to put a reason for that, what would you say? Converges because?
It's alternating and approaching zero.
It is an alternating series. And then I want you guys to use this kind of wording here, something along these lines. Alternating series and the terms decrease in absolute value to 0. All right, so what makes you so confident that the terms do decrease in absolute value to 0, Booker?
Because the bottom of the fraction is n factorial.
Yeah.
Is like that one's like the most rapidly increasing, and since it's in the denominator, that means the fraction's going to be getting closer to 0.
Yep. Yep, and the top is a 1, right? So that's just going to be held constant. What about this part right here? We didn't really address that part. That's the alternating part, yeah. So we're just looking at what the non-alternating part is doing. Is it headed towards 0 or not? Alexa, you had a question a second ago?
Yeah, well, I was just going to say pretty much exactly what Booker said, that you can tell because the factorial's in the denominator and that grows really quickly.
Yep.
But is there like a proof or a test you have to do, or can you just write that
No,
down?
it's okay for you just to recognize that. Make sure you say it, but we don't have to go beyond that to say because of this and because of that or anything like that.
Okay.
Yeah.
So this series, because it's n factorial in the denominator, it would converge even if it was pretty much anything else in the numerator besides like n,
Some other
x
factorial.
to the x, right?
Or x to the x.
Yeah.
Yeah. N to the n. Yeah.
N to the n.
Yep.
All right.
Agreed. Anybody else? Questions? Okay, awesome. So that's kind of what we did last time. So that's maybe a good review of last time. A couple of notes over there. It says, this alternating series remainder appears frequently. I don't know if I would say frequently, bless you. It appears. It happens sometimes. And the little box right there, we already dealt with that. So let's take a look here at parts B and C. So with parts B and C, it says approximate S5 by the first 5 terms. So our series is sigma from was it 1 to infinity? From 1 to infinity of -1 to to the n plus 1, 1 over n factorial. Okay, so what's the first term?
One.
1, yep. So you get negative 1 squared, so that's just 1, and then 1 over 1 factorial would just be 1. So 1. Plus, how about, I don't know if I'll put plus, because I know I got this alternating thing. Yeah, so it's going to be minus here. So minus, and then you guys said 1/2. All right, so that was plugging in a 2. How about plugging in a 3?
Plus 1/6.
Plus 1/6. Yep, 3 factorial is 3 times 2 times 1, so 1/6. I'm guessing the next term will be negative.
Minus 1/24.
Yep, 4 factorial is 1/24. We're supposed to use the first 5 terms, so our last term should be a plus 1 over 120. Okay. All right, so if we felt compelled to, we certainly could add all these up. I don't know if I feel super compelled to do that. It's going to be some number, right? You could do it. You want to do it real quick? Oh, come on. Heidi's head is saying this, but her face is saying this.
Yeah, it is.
Oh.
I think I just volunteered, actually.
All right, well, if we feel super energetic, maybe we'll go ahead and add those fractions up. But for now, let's leave it alone. Now, let's look at C. It says, use the alternating series remainder for what we just did there. We used 5 terms to get a partial sum to find the maximum error if we're using that to approximate the actual sum. So here's some good notation. Let's say something like this. The sum, represent with the letter S, minus S5, that's our partial sum using the first 5 terms. So that's our error. That's how far off we are. That has to be less than or equal to what concept?
The next term.
The next term, right? The first neglected term. Technically it's absolute value.
So n of 6.
So say again.
So you say it has to be less than or equal to S of 6?
Oh no, not S of 6, because S6 would represent the partial sum using the first 6 terms. You could say like the 6th term.
Yeah, how would you?
A of 6.
A sub 6, yeah. So we just got to calculate what that next term would be. What would it be?
Maybe 1 over.
But remember, we disregard the sign, right? Because we have those absolute values in there.
1 over 6 factorial.
1 over 6 factorial, sure. And what is 6 factorial?
720.
Yep. So 1 over 720. So the most we could be off is 1/720th. I mean, I don't know. That seems like a pretty small number, right? It's not quite as small as 1/1000th, but it's getting close. For whatever application you were using, you'd have to decide, is that a small enough error or is it not? What if you decided that that was way too big of an error? What could you go back and do?
More terms.
More terms, right? The more terms you have, the closer you would be to whatever the actual sum is. And as you can see, since the terms decrease in absolute value to 0, the more terms you have, then wouldn't the next term always be smaller? Be getting smaller and smaller and smaller. So the more terms you add in there, the closer you'd be to the actual sum. You can imagine, like, what if we had like 80 terms?
Very small.
Yeah, you'd be off by
Negligible.
1 over 81 factorial. And 81 factorial is gigantic, right?
Spaceship travel or something.
Who knows, right? Yeah, if we're talking about aerospace or astrospace, maybe we would want to be a little more precise. Who knows? Okay, so that's it. That's the general concept there with alternating series error bound. You look for that first neglected term, and that's it. A pretty simple, pretty convenient thing to do, at least in my opinion. Okay, so you guys remember, the kind of the silly concept. Oh, I'm sorry, Jack. Go ahead.
So the second part C says these actually estimate the actual sum. So would you write that as an inequality saying the
What's-
actual sum is less than or equal to 1 over 720 times the answer from B?
Well, you could, but I just said find the maximum error. So we found the maximum error. We said we did use an inequality right there. We said the error is less than or equal to the first neglected term. Make sense?
Yeah.
You could use this, if you wanted to, you could use this to essentially create a range for the actual sum. What you could do is you could just, go ahead and add these up, fulfill Heidi's dream, and add all those up. And then you could say, okay, so that's my partial sum. Then the actual sum would just be that partial sum plus or minus my error. You could create a range if you wanted to.
Yeah.
Yep, definitely. Okay, anybody else before we move on? Okay, so please remember just the silly idea that we've talked about, or at least that I've talked about in the past, of, we're cheering for these series to converge, right? We're wanting them to converge, and I'm just saying that's sort of a mindset just to kind of give us a focus on what we're doing. And so the alternating series, the alternating element makes it really easy for series to converge, right? So we kind of like the alternating element. We're going to take a look at one last thing in regard to this, and that is the concept of absolute versus conditional convergence. So if your parents say, hey, you're allowed to do this, or it's okay for you to do that, on one condition. Have you ever heard something like that?
It's the worst.
Right, so if you do this, then you can do that. They're giving you some kind of a condition to get the thing that you want. That make sense? Of course, life is full of those things, right? There's conditions everywhere. And so when we look at absolute and conditional convergence, we want to basically ask these series, are there any conditions to your convergence? Do you need some help? Or do you need something to kind of help you get there? And the only thing we've looked at to help them get there is this conditional, or the alternating element, right? That alternating element being in there. And so we're going to essentially in here, we're going to take that away and see if the series still converge. And if they do, we can make a judgment. And if they don't, then we can make a judgment on that. That make sense? Okay. So you can read the paragraph there. The absolute convergence test, if you will. So pretty simple deal here. If the series sigma absolute value of n converges, then the series a sub n also converges. So in other words, if we take that away, like if we take the alternating potentially pluses and minuses and all those things, if we take that away by putting the absolute values in there, and that still allows the series to converge, then if we allowed the plus minus to go in there, wouldn't that converge even better, so to speak? I mean, I'm being a little silly there. But yeah, so if you take away the thing that helped it converge, and it still converges, then we would actually call that absolutely convergent, right? It doesn't need the plus minuses. However, if we take away the absolute values, if we take away the plus minuses by putting the absolute value in there, we get a divergence. But then if we put the plus minus back in there and that allows the convergence, then that's a conditional convergence, right? Because the condition is the series needs the plus or minus. If the series doesn't need the plus or minus, it's absolutely convergent. If the series does need the plus minus, then it's called conditionally convergent. Does that make sense? Okay. And so we're going to run through a few examples here, and I'm hoping we'll get pretty quick at this. Okay, so let's take a look here at our examples, and this will be the last thing we do in our class today. So take a look at. Whoops. Hold on, I feel like something. This is really. So the first example is definitely not a classic alternating series. In fact, it's not even necessarily an alternating series. Let's take a look at why we would use this idea of absolute or conditional convergence with a series like number one. The denominator is just, guaranteed, what is the denominator going to be?
Positive.
It's got to be positive, right? Guys, sorry for the technological glitch there, but we're back and working, so mentally come on back. Thanks. But what's the top going to do?
Oh, it's gonna alternate.
Not necessarily going to alternate like plus, because there's going to be some pluses. Well, yeah, because I mean, sine of 1 should be positive. Sine of 2 should also be positive. Sine of 3 should also be positive, but sine of 4, negative. And so there's going to be some pluses and some minuses, right? And so for that reason, that's why we'd use it. This is not a typical looking, a series for something like this, but it's still worth doing. So let's consider absolute and conditional convergence. So knowing that the top is going to have some pluses and minuses, right? The denominator is n squared. So with those pluses and minuses, essentially we look at it and say, all right, the pluses and minuses are going to help this converge. But let's take a look at it absolutely. So if I said sigma from n equals 1 to infinity of absolute value of sine of n over n squared, let's think about what that would do. The top, this is the key, is understanding what sine does and what sine is. Guaranteed, the range for sine of n will be what? 1 to negative 1, right? So, but again, we're putting the absolute values on there. And so would it be fair to say that the range for absolute value of sine of n would be 0 to 1? Yeah. And so the top is going to be somewhere between 0 and 1, and the denominator is going to be n squared. So knowing what you know about the p-test and the integral test and the limit comparison test and all these tests that we've done before, if the top is somewhere between 0 and 1 and the denominator is n squared, what's going to happen? Not just go to 0, but is it converge or diverge?
Converge.
It's going to converge, right? In your own mind, like what kind of test are you thinking? What's the simplest test to consider that? Well, the nth term does not tell us convergence, right? The nth term does not. The p-test, right? What's the p-value?
Well, P is bigger than 2 and
P is 2, which is
bigger than 1.
yeah, so you'd get a convergence. So in other words, if I take away all the pluses and the minuses and I just have all pluses, this series still converges, doesn't it? So I would say that this series is absolutely convergent. Because whether those pluses or minuses are there doesn't really matter. You're still going to get a convergent series because essentially of that p-test concept that we just talked about. That makes sense?
Yeah.
Yeah.
When you explain that, do you say like is absolutely convergent because of the p-test?
You know what? I'm not going to really push that hard with your explanations here.
Okay.
I'm going to be looking for, can you identify what's going on and draw a good conclusion. That's about it.
Cool.
Okay, let's try a few others. You guys can see them in front of you, numbers 2 and 3. Okay, so take a look at number 2. Negative 1 to the n plus 1 over n. This is a more typical looking series, right? As far as the alternating stuff. And the signs on the terms are going to go plus minus, plus minus, plus minus. But let's consider the absolute or conditional convergence. If I did sigma from 1 to infinity, and I put the absolute value on there, then what is that absolute value effectively going to do?
Get rid of all the minuses.
Yes.
Yeah, all the minuses are gone. So you could think of this then as sigma from 1 to infinity of 1 over n, right? The top is either going to be a plus or minus 1, but with the absolute values, it guarantees that the top will just be a 1. Okay, so then what does that series do? It's harmonic, which diverges. So if you take away the pluses and the minuses, the series diverges, right? But if you allow the plus or minuses to be in there, the series converges still, right? Because of the alternating series test. So as far as absolute or conditional convergent, what's your judgment? It's conditional. So you'd say this series is conditionally convergent. So it only converges if you allow it to have the plus or minus signs, the alternating parts. Is making sense? Any questions? Okay. Take a look at number 3. Negative 1 to the n factorial, all over 2 to the n. So let's make a judgment on that series as far as absolute or conditional convergence. So when you're considering this, the first step is always to take away the plus minus and make them all plus. Any thoughts on this one?
Divergent.
It diverges, doesn't it? It's none of the above. It's divergent. Good.
What,
Nice job. We talk about why. Go ahead.
what like test would you use to explain that n factorial?
AST doesn't actually prove divergence.
Like, how would you explain that? Because, I mean, we know that n factorial is gonna grow faster than 2 to the
Sure.
n. So how do we, like, is there a test to tell that?
Yep. David, question?
Would it be, can you do like, separate the n factorial over 2n and do the limit of that as n approaches infinity?
So it'd be the nth term test.
Yeah.
Yeah. The answer to your question is nth term test. So I would say, if we're looking at this, we'd say, all right, limit as n goes to infinity
It's not.
of n factorial over 2 to the n. That is definitely not 0.
But it's infinity.
It's infinity, right? Because for the reason you suggested, that n factorial grows faster than 2 to the n eventually.
L'Hopital's?
You're looking at it as a whole.
No, it's not L'Hopital's. It's just the simple fact that this limit, the nth term test, does not give you 0. If the nth term does not go to 0, that's automatically you stop into the game, the series diverges to infinity.
That's when we have to use not comparison things, but like the tiers.
Like, you're looking at this as a whole.
To me, that's where it makes it super easy to the ranking thing.
Yeah.
Yeah, you look at the rankings, you're like factorial, faster than exponential. And so you know the nth term goes to infinity. So to me, this is where that, hopefully if you go back and remember those, makes this one super fast. So, okay, so yeah, we would say series diverges. And if you had to list a reason, you'd say nth term test.
Is it absolute?
So divergence is just divergence. There is no absolute or conditional. Any other questions?
So-
Wait, she said, yes.
So the alternating part of it doesn't make it converge?
No. So with the alternating element is very helpful, but the terms have to decrease in absolute value to 0 in order for the alternating element to allow the series to converge. Like if we looked at this on a graph, if we started graphing the terms, the first term would be 1, positive 1. So something like that. And then the second term, let's see here, so we plug in a 1, we would get negative 1 over 2. So, at first this would look like maybe it's going to converge, right? Because you'd get, you do something a little closer. But pretty quickly, so if we plug in a 2, that would be positive 1/2. So that would be about here. Come on, computer, you can do it. Keeps on wanting me to give me some other feature there. But as soon as you get to 3, let's see here. No, not quite. So it's actually, as soon as you get to 3, you can start to see it. Because those are 1/2. If you plug in a 3, you get negative 2/3. So, or is it negative? Yeah, negative 6/9. 6/8. Those are negative 3/4. There we go. You can see it a little bit more clearly. It's starting to move away from the x-axis. And then you plug in a 4, and you're going to get 12 16. So that's 24/16. Thank you. So that now we're over 1. So now we're at 1.5. And so we're starting to get further and further away. And so we're going to just start to see this. So even though they're, the terms are alternating sides of the x-axis, they're getting further and further away. So, yeah. Alexi, question.
So one thing I'm just a little bit confused on is like everything that we've done makes sense, but how do we know when to determine if it's like conditionally convergent, if that makes sense?
Like how would you know to check that?
Yeah, like for
So
number
you'd be
2.
prompted.
Okay.
You'd be prompted. So like the instructions here I think said, consider absolute or conditional
Oh, yeah,
convergence.
okay.
So like I can imagine on a quiz or test, it would say, I can see multiple choice written all over this, right? So it would say something like, which of the following series are conditionally convergent? And it would list out, some series, and you have to say, well, that one is divergent, and that one is absolutely convergent. Oh, that's the only one that's conditionally convergent, or something along those lines.
But like, so number 2 that we did, the example,
Uh-huh.
if it hadn't told us to evaluate for absolute convergence or conditional convergence,
Right.
we've just done the test that we looked at here.
AST.
series,
Yep, you'd say
and
converges by the AST. Yep. Exactly. Good question. Okay, we got a few more. Let's try those. So numbers 4 and 5. Number 4 looks ultra scary.
Oh, it does.
But take a minute and just analyze for a second. You've got -1 to the n over n plus 1, or n times n plus 1 over 2.
It's just alternating.
It's just an alternating element. Like that whole top part is just an alternating element. That's it. It's a complicated one for sure, how the signs are going to work. But that's all it is. Just an alternating element. So as you consider the conditional or absolute convergence, we would just say, hey, you know, absolute value it ends up just making that alternating part go away. So consider that. Okay, so what do you guys think? If you take away the alternating part, will this series converge or diverge? Converges. Let's go back in time a little bit. What kind of a series is 1 over 3 to the n? Geometric. Yep, the common ratio is between -1 and 1. Yep. And so we go all the way back to the original question, conditional or absolute. Is this conditional or absolute?
Absolutely converges
Yep.
by way of GST.
Absolutely converges. Yep, because if you take away the plus minus stuff, you still get a nice geometric series that converges. Okay, so I'm going to leave maybe numbers 5 and 6 up to you guys. I'll move this a little bit for you, and I'll let you guys try 5 and 6 on your own.
Right now?
Yep, go for it. Just shout it out. What do you think?
Conditional convergence.
Conditionally convergent. Okay. Any point of disagreement on that?
Well, me and Booker just are confused still how you tell the difference between that and just purely divergent in this case.
Okay. So if we do this, if we say sigma from 1 to infinity of absolute value of -1 to the n over root n, essentially what that does is it just takes away the plus minus, right?
Just 1 over n.
Yep. So sigma 1 over n to the 1/2. And if you wanted to, analyze this and list out your reasons, you would say that series, the one that I just wrote up there, that one diverges, right? Because of the p-test, right? But then when you go back to this, you say, well, originally this thing did have the alternating element, right? Plus minus plus minus. Or I guess technically minus plus minus plus on this one. So then you say, okay, well it did have alternating, terms there, right? So then you ask yourself, well, what does the AST say about that? Well, the AST says, if the terms decrease in absolute value to 0. So if you think about 1 over root n, as n gets bigger and bigger and bigger, won't the terms still go to 0? They'll get to 0 pretty slowly, but they'll get to 0. And so with the alternating element, it really doesn't matter how fast or slow the terms get to 0. As long as the term gets to 0 and you combine that with plus minus, you do get convergence. So in other words, with the plus minus stuff, we get convergence. Without the plus minus stuff, we get divergence. That means you guys were right, we are conditionally convergent on this one. Make sense? Okay. And then how about number 6 as far as an answer goes? What did you guys come up with? Shout it out. Conditional. Any disagreement on that?
Can we go over why?
Sure. So conditionally convergent,
The AST is pretty easy with this one.
the AST is what?
Pretty easy with this one, but
Right. So if you say n equals 1 to infinity, you take away the alternating element, and then we look at it in terms of just that, we just have to say this would be 1 over ln of n plus 1. So you start to look at this in terms of speed of getting to 0, right? Isn't it true that ln, like the family of logarithms, gets there slowest? I think that's the slowest classification, the logarithm stuff. And so you'd have to say, well,
But 1's not in the middle.
but what?
But the one's not getting to infinity ever, so it's like a constant over something that's
Right.
going slowly.
So the nth term, is headed towards 0, right?
Mhm.
But then when you look at, the speed of this, and this is where the relative growth rates, rankings things, I think makes a big difference for us. Because to do another test, like a integral test, I don't know, it's going to be tough to do this quantitatively, right? Instead of just looking at the rankings thing. I think the rankings is where you'd want to go here and say, well, this gets to 0, these terms get to 0 even slower than 1 over n. You could almost you probably could do a comparison test. I don't know about a limit comparison, but you could do a comparison test for sure. It's probably where you'd have to go. So if 1 over n doesn't get there fast enough, then this definitely doesn't get there fast enough, right? And so you'd say, well, this in and of itself diverges, but the terms do head to 0. And so because, you really have to consider that the alternating element was there, since the terms do head to 0, it would converge conditionally. You take away that plus minus thing, then it definitely diverges. So we'd arrive at conditionally convergent.
Why
Alexi.
does that diverge again? I still confused.
So I would do a comparison test. So I would say sigma, I haven't actually worked the numbers through here to be sure that I have the exact right numbers, but sigma from 1 to infinity of 1 over n diverges, right? And then we can analyze this in a second, see if this is really true, but 0 is less than 1 over n plus 1, which is less than 1 over n. Oops. Let me get the right things in here. Sorry. 0 is less than 1 over ln of n plus 1, which is less than 1 over n. We could find this to be true on some interval that's contained within 1 to infinity.
Yeah.
So I would say that because 1 over n diverges, 1 over ln of n plus 1 also diverges by comparison.
This is probably really dumb, but is ln of n plus 1 always less than 1 over n?
Well, that's why I said I'd have to double check my numbers to figure out which interval that is, but I can guarantee you that somewhere on the interval 1 to infinity, it might be 5 to infinity or 10 to infinity, or it might be 1 to infinity. I have to go through and calculate the numbers to see exactly which interval that applies to. I guarantee, though, it's going to be from some positive number up to infinity that'll be true. So I could use comparison to do that. But to be honest with you, I would encourage you to think of this in terms of the relative growth rates thing, with ln growing slower than any polynomial. So, okay, that's it.